Hi, a very good morning to all of you. So I'll give a few seconds for a couple of people to join in. Let's give a minute for people to join in. Hey all. Right. I think we can start. Okay. Right. So I think until people are getting in, it's been a very different experience. Even though we have all sorts of learning from home, working from home, it's usually for about a day or two that we usually put working from home, but it's been now nearly 3 weeks, a little more than that, and quite bored, and at the same time feeling very lazy also, but we have a lot of work, and I hope you guys are doing good too. Most important thing, stay home, be safe, right? Okay, I think we'll kickstart. So a very good morning again to all of you tuning in for the live session. And my name is Chatusha, and I work as a consultant technology for Virtusa Corporation. And it's been really lovely to have a live session. And this is actually one of the first sessions that we are going to do on Insta Live. And the key audience of this whole session is basically students, A-level students, undergraduates, recent graduates, and not only that, anyone who's really interested in the particular subject. So that is our primary target audience. And we want you all to engage with us, ask questions during the session, and even afterwards, if there's anything, I'll also get back to you, ask questions, and let us know the topics that you're really interested in terms of technology, right? Good folks at Virtusa are willing to engage with you and teach you, share their experiences on various things, be it cloud computing, blockchain, microservices, whatnot, right? So the whole idea from a corporate perspective is to engage with the young blood who are staying at home watching movies, right? So it will be a very interesting series of sessions where you will get to learn a lot about technology, what you have been learning, and most importantly, how we apply things in the real business context, in the business world as a company, right? And so first of all, I'll give a brief introduction about the session, about the theme of the session, or rather the nature of the session. And then we'll go a little bit deeper into the fundamental principles of AI and ML, and we'll talk more about the current applications that you yourself know in your day-to-day activities that are using AI and ML extensively. And not only that, certain things that you wouldn't have even imagined that use AI and ML. And at last, I'll share my experience about what it means to know an AI and ML when you come for an interview, when you're applying for a job, and how to really learn anything, right, in the technology field. So I'll give you a little bit of perspective into that as well, right? Okay, so this particular session is not exactly a very conventional introduction to AI and ML. It's rather more in line with the fundamental principles that form the very foundation of artificial intelligence, machine learning, etc. Right? And the reason, the real motivation behind this session to take that sort of a theme is that even when we do interviews and when we talk to a lot of new kids coming from universities, they're brilliant. They're brilliant at coding, right? They're very good at calling functions, or when you throw a problem at them, AI. I have seen a lot of people import PyTorch, TensorFlow, and they implement a neural network, sometimes go for a deep learning and all that, or maybe import scikit-learn and then get an SVM, etc. But if you really ask, how did you define the layers? What are the activation functions you used, or what's the rationale behind the regularization that went into your solution, right? They actually run out of words. The reason being, they are very good at calling functions and doing the coding and implementing it, but when it comes to the underlying principles, a lot of us don't really understand, right? So that is the primary objective of this session, to highlight the underlying principles behind AI and ML. This is not about coding. I will not get into coding or share my screen or do anything with regard to that. Okay, cool. So a lot of these sessions start with the simple question: what is artificial intelligence, right? I don't want to start with that question because it's not the real question. There's a very fundamental question behind it. Okay, what is intelligence to begin with? What does it mean by intelligence? If an agent is intelligent, what does it really mean, right? So if you take various fields, psychology, sociology, history, and many other arenas, all the experts have very different definitions for what they mean by intelligence, right? But if you put everything together, if you collate the ideas, you will end up with a very abstract sense of what intelligence is. It's simply you gather information, you perceive and understand information, and you build and retain knowledge or a capability which you can go and deploy in a different context or in a different dynamic environment. You gather information, you retain a knowledge or a capability from that information, and you go and put it in a different context to get a conclusion, to make an inference, right? So if you actually go to the history of the human evolution, right? I would like to quote one historian, Yuval Noah Harari, right? From 150,000 years ago up to now, how the human mind, the human body and the human mind has evolved. It's very interesting. So he breaks it down into 3 revolutions, right? We started off as the chimpanzees, the monkey family, right? And then became hunter-gatherers. For that, the cognitive revolution happened. People started getting together. People started coordinating with other people. They hunted together. They went on killing animals and sharing their meat, etc. Right? So they gathered a lot of information from the surrounding. They developed the capability and they applied it in different contexts. Say, for example, today a herd got together. They tried to kill a huge animal, but in the process they failed. Maybe a lot of people got killed. But tomorrow they're going to learn from that experience and they're going to do something different. They invented fire and they invented a lot of different tools from that experience that they have gathered. So this is a form of improvement in intelligence. Then came the second revolution, the agricultural revolution, right? With the drastic growth in the population, it was not viable for us to hunt anymore and then kill, etc. So people had to resolve into growing their own wheat and etc. Right? So they started this coordination that existed among people became more complex. They worked together in paddy fields, they forecasted their yield, they stored their yield, they did computations, they did calculations, so they gathered information from the surrounding, retained knowledge, and applied it in different contexts, right? So the same counting systems that they used to count the number of days was also used to count the kilograms or tons of wheat they produced per yield, right? So they applied it in different contexts. Then came the third revolution, the scientific revolution, right? And as we all know, we are living in a much more advanced society, and our lives have become very complicated, right? We work with financial systems, we work with computer systems, we go to the moon, we send rockets to Mars, etc., right? After the Industrial Revolution. And even today, what we do on a daily basis, right, is actually gathering information, retaining that knowledge, building a capability, and applying it in a different contexts. So all in all, when you put together, this is basically the intelligence that we call, right? And if we can get an artificial agent, say a computer program, to mimic this human behavior, to gather information, to develop a capability, knowledge, and apply it in a different dynamic environment, we say that we have implemented artificial intelligence, right? So the basic question that you need to focus on is not actually what artificial intelligence is, but rather what is intelligence, right? Let me put it in a different sense also, because this whole concept is very important for you to understand when you're working with different problems. For example, right now you're looking at a screen, you're looking at me. You can see that I'm talking, a person, I'm wearing spectacles, there's an earphone. You understand the context, and most importantly, you understand the language that's coming out of me, right? And you give very little credit to yourself for being able to do that. But if you actually, with all the due respect, get someone suffering from Down syndrome or some sort of a mental impairment right in front of the screen, the person would not be able to understand what's going on. He or she might not be able to understand whether I am another human being, etc. So we take this natural ability for us to gather information and make conclusions, right, to process it. We give very little credit to it. Why? Because we have been training this model, we have been training this brain for a very long time. 18 years, 20, 25, or even more, right? Yes. And right throughout that history, this model has been training to do all these things that we do in a day-to-day basis without paying attention to any of it. Understood? So that is essentially how important the intelligence is, right? And I would like to share something. Okay. Right. So one of the things that we need to talk about next is the concept of modeling, right? So when you say modeling, when you say fashion models, the beautiful image comes to you, you know, a beautiful man or a woman walking down the stage, showing off clothes and all that. But have you ever wondered, what is this fashion modeling? What do they actually do? What is the end result of it? If you actually look at it from an abstract sense, right, what they do is they essentially take the input, which is the dress, they wear it, and they show you the output, right? So they give you a sense of this is how you're going to look like if you wear it. Of course, it's not the case, but that's the objective of fashion modeling, right? So the same principle, we can go and apply it in mathematics. There's a brilliant concept called mathematical modeling. What it essentially does is, when you have a certain problem, you model it, you can give it the inputs, and you can say, this is how your output is going to look like. Say, for example, a weather model, right? So today I'm going to upload all the parameters, my input variables, the temperature, the humidity, the wind flows, blah, 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 whatnot, all the parameters into a weather model, so that I can predict this is what the weather is going to look like tomorrow. Is it going to rain? Is it going to be cloudy? What sort of a temperature distribution can we expect in the country, etc. Right? So this is a model to which, when you give the input, it shows you the output. Building an artificial intelligence, an AI or an ML model, machine learning, I'll come to the definitions of those two terms a little later. What we are essentially trying to do is, we are trying to model the problem so that when you give an input, it gives us a prediction, an output. This is how it's going to be. Right? So essentially, we are modeling a problem. So the fundamental idea behind a machine learning model is quite similar to what fashion models do by wearing a dress. Right? Let's go for an example. Let's take, I'm pretty sure all of you would have heard about autonomous self-driving cars, right? It sounds very fancy. It is, right? Tesla is coming up with it, Toyota is doing it, and a lot of car manufacturers are actually going ahead with these self-driving cars, and there are a lot of Sri Lankan researchers also in the field, right? So what is this problem, right? It's exactly trying to mimic what you would do if you were behind the wheel, right? If you're the person who's driving, the model or the set of models or the complex intricate system is designed to replicate what you do, your set of actions, right? So when you are presented with a problem like that, at first you need to figure out, you cannot look at the entire problem at once. You're not going to solve any problem just by looking at the whole problem at once, right? First you look at a bird's eye view of what the problem is. Then you try to break it down into different pieces, right? So the puzzle has different puzzles now, smaller pieces. Say, for example, first thing you need to do in a self-driving car, you need to understand the environment, right? You should be able to see what's ahead in the windscreen or the road ahead, side mirrors, what's at the back, right? And not only that, we also use a lot of different sensors in these cars. You have proximity sensors, LiDAR systems, etc., right? So all these sensors basically try to get an understanding of what the surrounding is, number one. How does it look like in front of you and around, right? Then comes, what are the things in your environment, right? You try to understand the objects. Are there people walking by? Is there a traffic light in front of me? Is there a vehicle in front of me, right? And or else, is there another vehicle to my right, right? So when I look at my rear view mirror, right? Is there another vehicle that's approaching me at a faster rate, right? So then you try to understand the environment. What are the objects? You classify these objects into different things. You are not exactly very much worried about a building that's actually to your right, right? You know the building is not going to move and that it's into your right. But you're very much worried about a person who's trying to cross the road right in front. You know that it is a person. You know that the intention of the person looks like that he or she wants to cross the road, right? So that means you're definitely going into direct contact. So then you interpret your environment. And the next thing, you have to determine the motions, right? As I said, is the person trying to move? What about the vehicle in front? Is it actually trying to move forward, or is the vehicle in front breaking down, right? you're trying to interpret the dynamics of the surrounding. And fourth part of it is actually you decide what your reaction is. Now this is very, very advanced, right? Why I am saying that it's advanced is take two people, right? So all the people who are in this live video right now, two of you would not react the exact same way if you were behind the wheel in the exact same circumstance, right? Some of you might step on the pedal, some of you might not take it for granted, some of you might turn the wheel, etc. So these reactions are very, very complex. But then you as a driver, you have been trained for a very long time, and that you have a very advanced intelligence, you actually take it for granted, right? So what have I essentially done? I have broken down the concept of self-driving cars into different components. First, you should be able to see the surrounding. Then you should be able to interpret the objects in the surrounding. Then you should be able to interpret the dynamics of the objects in the surrounding. Are they moving? Is it a traffic light? Is it red? Etc. Right? And then you're trying to decide what your reaction is going to be. Right? So now the whole problem of self-driving cars has been broken down into 4 different separate problems. Right? Separate problems, and you need to solve each of these problems separately. Of course, they are interconnected, but you approach them, you attack them in 4 different ways. So this is, in a nutshell, how you would break down a problem into different sub-problems. And then you go into each and every piece of that puzzle and you go deep inside that. Okay? This is a very, very important concept for you all to understand when you are entering AI and ML arena. Right. Then, okay. So let's get into a couple of words, right? I'm pretty sure all of you in the live stream would have heard the word artificial intelligence. Well, that's why you actually joined, right? You have heard the word machine learning, I'm pretty sure. You have heard the word deep learning, I'm quite sure, right? But what's the difference? What do they actually mean? In a nutshell, as you can see on this image, the bigger umbrella of everything is artificial intelligence. The entire spectrum of fields under this, the bigger picture, we call it as artificial intelligence. Systems which can gather information, build the knowledge, retain it, and apply it in different contexts. Okay? A subset of artificial intelligence is machine learning. A subset of machine learning is deep learning. Now the meaning of this is there are artificial intelligence systems which are not machine learning. There are machine learning systems which are not deep learning. Right? I hope you can get that understanding by the subset principle that you see on the screen. Okay? So when you say AI, right, you gather information, you develop a knowledge and go and apply it. This can be done using a very advanced rule engine, right? Say for example, I'm building a system and I know each and every possibility that can occur in the system, right? So what do? I write a rule. If this happens, do this. If this happens, do this. If this happens, do this. So it's a very complex, intricate system of rules, right? So essentially, it's not machine learning, but it's also intelligent. It can interpret and take a decision accordingly. But it entirely relies on the human expert who has written the rule engine, right? This actually works in a lot of different contexts. Like a lot of the applications that we are seeing right now, very simple things. They're all they are all in a way sort of intelligent systems, but rule engines. Then comes a different problem. say the amount of possibilities are huge. For example, let me take the game of Go, right? It's a Chinese game, and if you take the number of, now if you play tennis or any other game, Atari for example, the number of possibilities are actually finite. It's quite limited, right? But if you take the if you take something like Go, the number of possibilities are near infinite. I'm not saying infinite, but near infinite, right? So it's very difficult for a human being to write a rule engine for a system to be able to do that. In such cases, we feed in the data to an algorithm, to an application, and we get the machine, the algorithm or the application to learn from that data. This is essentially machine learning, right? So I'll come to different parts of machine learning next. And then comes deep learning, right? Deep learning is actually not very, it doesn't have a huge history, right? So it came into existence a decade or little more than that ago, right? It's an advanced form of machine learning, let's say, right? So I'll come to deep learning and neural networks as well a little bit later on, right? So in a nutshell, the bigger picture or the umbrella under which all these things fall is called artificial intelligence. Systems which can gather information, retain knowledge, and apply it in different contexts. Under that, when you feed in data to an application and get the machine to learn from that data and develop that knowledge or intelligence, we call it machine learning. And an advanced form of machine learning is deep learning, where you can where you need very advanced computations to solve advanced problems, right? So artificial intelligence, a subset of which is machine learning, and a subset of machine learning is deep learning, right? I hope that's clear. Okay. Then the kind of problems that we actually solve in AI and ML world, right? So essentially there are two kinds of problems. One would be, in simply we call it regression, right? What you're trying to do, you're trying to predict a value. Say example, you take the stock value of Virtusa in the last couple of months and you try to predict what it's going to be like tomorrow or next month, right? So that is one. You are trying to predict a value. And then comes classification, right? So classification is essentially you're trying to group data into different buckets, right? These kinds of things look like this and these kinds of things look like this, and they are different by nature. So you group data, and that is essentially called classification. Of course, there are we can go a little bit deep into clustering, etc. But these are, in a nutshell, the two main problems that we try to solve in the AI/ML world, right? So when you take a real problem, right, definitely the problem will have to do with numbers, right? If it is numbers, it's good, because we all know that computer is a machine which can process numbers. We might be looking at sound, right? When I'm talking right now, this gets converted to a digital signal, and at your end it gets converted to sound back again, right? And then images. You see a person talking right in front of you on a screen. You're looking at an image. You can interpret that. You can interpret my voice also, right? And you can interpret the text. So I'm guessing you can see a couple of comments going down there, and when I share a photo or a PPT slide, you can see the text in that, right? So the human brain can actually process sound, text, images, These are very basic things that we do, right? But actually it requires a lot of intelligence, a lot of computations to be able to process these stories. A computer can never ever process sound, images, or text, right? They have no context or no meaning to a computer, okay? A computer always processes a mathematical representation of the text, a mathematical representation of the image, and a mathematical representation of the voice or sound. Always these things are converted to a vectorized form. We call it vectorized images or word embeddings, etc. Right? I'm not going deep into those things, but essentially we convert all these things into a mathematical representation. You take an image, and the pixel distribution is basically a mathematical representation of that image, for example, right? So a computer always works with these things. And in the world of AI and ML, how you convert your images or voice or especially text into these mathematical representations is a very daunting task. It's something that requires meticulous planning and understanding of the problem, right? So that is something that you all should keep in mind. Okay, let's move into, give me a second. Right, so let's move into the types of machine learning that you come across, right? For some of you who would have already got some sort of an experience about AI and ML, you kind of would have heard these words for sure, right? So essentially there are three types of machine learning, right? There are more types, but at a very high level, I'm going to say there are three types of machine learning. One, supervised learning, unsupervised learning, and quite recently we are exposed to reinforcement learning. Of course, there are other ways, like other categories like semi-supervised learning, etc. But for the moment, let's forget about data augmentation, semi-supervised learning, and all. Let's focus on supervised, unsupervised, and reinforcement learning, right? So out of this, what is supervised learning? Imagine that you have a child, right? You would have played with a child. How does a child learn? How do you teach a child, a very, very young infant, right? Right throughout the process, how do you groom an infant? Essentially, you teach the person what is right, what is wrong, what is blue, what is red, what is a triangle, what is a circle, right? So when you feed in, when you have to classify two types of fruits, apples and oranges, right? You feed in tons and tons of images of apples and oranges into a system, right? And these images are labeled. All the apples will be labeled as apples, all the orange ones will be labeled as oranges. And you get the algorithm to learn the difference, right? You get the child to learn. This is blue, this is red, this is green, this is black, this is a circle, this is a triangle, right? You tell him or her what it is, right? Then with time, the model learns from these data, from these experiences, and later, when you give in a image of an apple without saying that it's an apple, it will be able to classify the image as an apple. You give a child a triangle without saying that this is a triangle, he or she with time will be able to say this is a triangle, right? This is a supervised form of learning. You supervise how the person or the application is learning. You teach it what needs to be done, right? This is essentially supervised learning. There are a lot of different algorithms that come under supervised learning, from support vector machines to CRFs to blah, blah, blah. Markov models, you can go deep into those algorithms. But all these things are focused on labeled data. The application learns from labeled data. Clear? The second type, unsupervised learning, right? So in unsupervised learning, you don't teach the child that this is a triangle, this is a circle, that this is an orange, that this is an apple. You don't teach the application what it is. These images are not labeled, right? But when you feed in tons and tons of images, with time, the application will be able to differentiate these two. It will be able to distinguish the differences between apples and oranges. But it might not know, it will not know that this is an apple or an orange. It won't be able to label, okay, here are your apples, here are your oranges, no. But this is your first set of data, this is your second set of data, right? That will be the output essentially. You're not telling it what it is, but you get the algorithm to learn by letting it understand the difference between the data. This is essentially unsupervised learning. We are looking at k-means, LDA, latent dirichlet allocation, principal PCAs, principal component analysis, etc. Right? So all these algorithms, you don't necessarily give the label, but it distinguishes the difference, or else it works with the data to learn something, right? So I'll touch a little bit about the LDA and PCA later, maybe depending on the questions, right? Then comes reinforcement learning. So this is mainly in the arena of game AI, and it's been used in many different contexts as well. If you take the game of Atari, right? You know, the platform is moving and there's a ball which goes up and hitting the blocks, right? What it does is, what reinforcement learning technically means is that you get the agent, you get the algorithm to play the game on its own. You tell the algorithm, okay, these are your possible moves. You can move to your left, you can move to your right, but that's it, right? That's all I'm going to teach you. Then you give it an objective. I'll come to this objective in a little bit more detail later. Next, you give it an objective. Your objective is to break the maximum number of blocks on top in the game, right? Let's take a very basic game, right? You can make it more advanced, not all the blocks, but a particular set of blocks, likewise, right? So the algorithm keeps on playing the game. It moves to the right, it moves to the left, it hits the ball, it misses the ball, on and on it goes. And then when you break blocks, your reward, your objective is being achieved, right? And you give this objective in the form of a reward function. When you score, your score can be basically the reward function. When you score more and more, your reward increases, the algorithm is happy. So it knows that these are the set of movements that I need to do to be happy, or else to get the maximum reward, right? So your reward function keeps increasing. So it learns these set of actions on its own. Now this is actually a pretty advanced form of machine learning. But this is what's being used in DeepMind's AlphaGo, right? You know, I talked about Go. So quite recently, the algorithm developed by DeepMind, which is a subsidiary of Google. DeepMind, they developed the algorithm AlphaGo, which beat the best Go player in the world, right? So I think he was a Chinese player who was really good at it, renowned Go player. He was actually beaten by this. See, the interesting idea is this, right? In supervised learning, you teach the algorithm what you know. This is oranges, this is apples. In unsupervised learning, you give it data. You're the one who's giving it data for it to learn. Right? So it entirely learns on your data. In both these circumstances, at an abstract level, now you will realize that there's no way the algorithm will exceed the human capability. There are instances where it has done better than humans, but let's say at an abstract level, it's very difficult for the algorithm to go beyond the human intelligence, because you're the one who's feeding it data and you're the ones who teach it, right? Label it. In reinforcement learning, what essentially happens is you get the algorithm to play, you get the algorithm to do actions. All you say is, these are your axis of free movement. This is what you can do, and this is your objective, your reward, right? And it keeps on playing using different methods, different combination of actions. It keeps on playing and then learns. So essentially, you can see that reinforcement has the ability to actually exceed the human intelligence in a particular task, right? I'm not saying metrics, robots are going to take over the universe. That's a different topic for another day, general intelligence, etc. But it has, in this particular task, reinforcement learning has the ability to exceed the human capability, right? So it's difficult for the other two to do that, but this has, right? So this is a very advanced form of machine learning algorithms, not only in game AIs, but you also see it in certain recommendation engines, right? Right now you're using Netflix and Xbox and all that. So and even Facebook, Alibaba, AliExpress and eBay, all these sites, right? They have recommendation engines. We'll come to that a little bit later. A lot of these recommendation engines are actually reinforcement learning algorithms, which play the game behind, okay? Right. Okay, and let's move into different architectures of machine learning, right? So essentially, in a very abstract level, at a very high level, there are two different architectures of machine learning, not types of machine learning, but two different architectures of machine learning. Number one, we call it statistical learning or statistical modeling. This, as you can see in the screen, right? Statistical ML models. So you can start with simple regressions, right? Simple lines, y equals mx plus c, right? Or else you can talk about planes, x plus by plus cz plus d equals 0, right? So all these statistical models, they do the same. They learn from the data, they develop an equation or a function or a model which can later be used to get the output for a different set of input data, okay? But the interesting part is, in all these things, you can actually see what the equations are. You know the exact computations that go behind it, right? These are pure mathematical models, right? You see very complex equations, but nevertheless, they are equations which you can see, okay? And this is one form of ML, or we call it statistical learning. The other is actually what you would have heard of mostly, right? Oops. Okay. Next, the other form of architecture is basically the neural network, right? Now, the whole concept of neural networks is inspired by how our brain works. As I mentioned at the very beginning, what are we trying to do? We are trying to mimic human behavior. We are trying to replicate what a human would do in all these circumstances, right? So there's absolutely no better way to do it other than to build an application which works just like how the building blocks of our brain works, right? We all would have heard about neurons, right? So what essentially happens is you get a set of data. Let me show you. Yes, right. So at the top you see the biological neuron, right? So you get electrical signals from dendrites, and you get the nucleus, which kind of processes it to some extent. It goes to the axon or the tail, and then it exits and it goes to another neuron, right? And this neuron also gets its input signals from another neuron, right? So this is essentially the brain structure. If you take the human brain, roughly around 80 to 86 billion neurons are present, if I'm not mistaken, right? And then these artificial neurons are designed to work the exact same way. As you can see at the bottom, right? It takes in a signal or a particular number from a neuron right in front of it, and it multiplies this number by a particular weight, A1, A2, A3, as you can see here. And then it goes to a particular function. Now this we call an activation function. I'm not getting into details of it, but it's, let's say it's a mathematical function. It can be linear, it can be sigmoid, hyperbolic tangent, there are a couple of more options, right? And then it exits. What exits, it's also a number, right? So essentially, in a neural network, it's not just an equation, right? In statistical machine learning, it's always a mathematical function, right? You can see it, you can see the weights of everything, you can see the computations that go behind it. But a neural network is quite different. It's an intricate system or a network of numbers. So naturally, now you will be able to sense that now why are we going ahead with statistical learning? Because if you implement neural networks, right, they are much more advanced and you can get better results, right? There are pros and cons to both these approaches, right? When you're presented with a certain problem, right, you technically never start with the deep learning. Don't go import TensorFlow, PyTorch and start building your neural network, right? First you understand the problem, break it down into different pieces so that it's not one puzzle but you have a subset of puzzles. Then you try to attack each and every puzzle, as I explained in the previous examples, right? You start off, usually it's always better to start off with a statistical model. Apply simple regression if it is about predicting a number. Try applying support vector machines if it is about simple classification. Try applying CRF or a conditional random field if you're looking at sequential labeling or sequential classification. I'm not getting into details of these things. Don't worry if you don't understand, but these are the fundamentals, right? And if the accuracy levels are not as expected, then move into a convolutional or a recurrent neural network or whatever. Go to a neural network, right? The idea is this. Both these have their pros and cons. And yes, the neural networks are usually more robust. They are usually more accurate. As you can see, they work very, very similar to how your brain works, right? But you need a lot of data and processing power to build a neural network. And it takes time to make an inference or come to a conclusion. Whereas statistical models require relatively lesser number of data, right? Say for example, oranges and apples, right? Maybe you don't have 1 million images of oranges and apples. You only have around 50 or 100. You start off with a simple statistical classifier, failing upon which, and if you can find more and more data, you move into the neural network space, right? So both these have their own pros and cons. Statistical models are usually much faster. They require less processing power and less data to make an inference, whereas neural networks are more robust, more accurate, but they are very hard to train. You need a lot of processing power. There's another aspect to this as well called ML interpretability. I am not getting deep into that because usually in our line of work, when we apply AI systems in insurance companies, in banks, etc., we should be able to explain the decision taken by an ML model, right? Whereas this explainability is very difficult when what's being deployed is a neural network or a deep learning system. It's quite easy, statistical and more intuitive to understand and interpret a decision if you have used statistical model, right? So these are the two main architectures, and these are the primary pros and cons in using these two. Give me 1 second. Right, I think we are open for Q&As as well. If you have any question whatsoever, put it as a comment, and let's see if it is if it's something that we can discuss right now. Definitely we'll get into it, or else you can always reach out to us from the page, drop a message, drop your question, and we'll have a discussion, right? Okay. Right, so there's another very important, now we to do a bit of a summary about what we have done so far, right? We learned about what is intelligence, right? And we learned about breaking down a complex problem into different problems, right? We talked about self-driving cars and all that, how you break a problem into different pieces of the puzzle, how AI and ML works with, how computers work with images, audio, voice, and all that, right? Because the whole vectorization and the mathematical representation of it. We learned about the types of machine learning: supervised, unsupervised, and reinforcement learning. Then we talked about the two different architectures of machine learning, primarily the statistical and the neural networks. Then we talked about the pros and cons in use in these two different architectures. Right, so let me check if there are any questions so far. Okay, as we go along, if there are any questions, doubts, or anything, just type it and send. Okay, right. So now we are getting into something quite interesting, right? How do you train a machine learning? How does it really work inside, right? These are very interesting questions to ask and even to talk about. So guys, if you just think about yourself, right? Do we really do things without an objective? Yes, we do some things which have absolutely no objective, but most of the time we need an objective to do something in life, right? There's something that you're willing to achieve by doing it, right? So just like that, when you train an AI model, you give it an objective. This is what you're going to do, right? So let's take a very simple model. For example, we are looking at a simple regression, right? So in a regression, you have to come up with a line in order to suit the data, the best fit line, okay? So let's say ax plus by plus c equals 0, or else in other terms, y equals mx plus c. That's the term that all of you would have heard of, right? So there are two parameters in this equation, right, or in this line, which define it: m, or the gradient, and c, which is the constant, okay? So when you know your m and c, you basically know your line. That's it, okay? You can plot it in your data. Learning essentially means you're trying to figure out these parameters which define the function, okay? Which say in y equals mx plus c, you're trying to fit a curve. You move the curve, you try to fit all these curves and see what is your best m and best c combination, okay? So how do you determine whether it's the best or not? So when you have different plots of data, so let me put that Right, so as you can see on the top, right, so this is a simple regression that I'm trying to fit to different kinds of data. So now it's not the perfect line, right? You can see definitely there are dots above it and dots below it, data points basically. Okay, so all these data points which are not exactly on the line form an error. Okay, so we calculate this error. We can take the root mean square error, RMS, etc. We calculate an error and we define an error function to this algorithm. So look here, this is your error function. So whatever the lines that you come up with, this is the cumulative error when you put it against all the data points. So the objective, the natural objective of the machine learning is to minimize this error. So it figures out various different lines, various M's and C's and combinations, and tries to see what is the best combination which gives me the least root mean square or else the error. I'm not getting into what root mean square is and all that at this stage, but it's quite simple. Minimizing the error is the objective. Now recall I said in reinforcement learning, right, you define a reward function, right? When you're playing the game Atari, you move the platform left and right, and depending on the number of blocks you break, your score increases, right? When you play a game, any game, so that is your objective, right? You keep on scoring. So there, the objective is to maximize the reward function. In most of the cases, the objective of a machine learning is actually to minimize the error when you fit it to data. Okay, and it searches the entire space, entire feature space for different combinations of weights. That means M's and C's and different line combinations to see when it's hitting the best possible error or the least error. And when you have hit the least error, you are essentially looking at the best fit line for that particular set of data, right? So let me show you something. Yes, so as you can see on the screen in the left, it's very easy for the algorithm to converge because there's an absolute bottom and there's only one point in the bottom, right? So when you go across this space, at one point you are definitely going to come down. Okay, and these algorithms, there are separate algorithms, optimization algorithms, which are designed for weights to actually come down and find this minimum point, minimum error. What you see on the screen is basically error. But on the right side, you will see that it's not easy. It's a very complex space of errors, right? So the error function is very complex. You will see there are bumps. All of a sudden your error goes up. You have a very high error. And then there are certain places where your error is quite low, but that's not the absolute lowest possible error that you can achieve, right? And then there's this absolute lowest possible error. So you navigate this particular space and try to figure out, okay, what is the absolute or the minimum error that you can achieve with this particular function. So you always give an objective to an algorithm: minimize the error or maximize the reward function. And this is what it tries to do right throughout. Okay, right. Any questions so far? My friends are not supposed to be in this live session. Anyway, now let's. Now I think we have already come to the middle of the session. Now we'll get into a couple of very interesting applications of AI/ML in our day-to-day lives. Right? There are various different applications that use artificial intelligence, machine learning, etc. And some of them you might have an idea, okay, this is using AI, and in some